Hello, Rob.
Morning.
How are you feeling? You still okay? You think?
I've got a little bit of a runny nose and a cough, but nothing.
Okay.
And it's it's January, so
Yeah, exactly. Okay, yeah. Yeah, that's your view for your friends. In your quarantine, at least you get to see some faces.
morning all.
Good. You're missing someone, right? Michael. Yeah. 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 So did you guys get to look at functional derivatives? Any comments on it? Maybe you guys didn't get a chance to.
I haven't looked at it
Yeah. Because you guys must be doing other things too, right? It's not that. Have you guys done calculus of variations before?
yet. I don't know. I don't think so.
It may not show up in this style. Typically, it is done in slightly different format. At least methodology is different, but idea is the same. In some form, probably you must have done, all of you must have done it because Lagrangian mechanics uses this principle, if you want, how you satisfy or how you convince that is okay. I think I finish this. Okay, so now there's my okay. I was thinking I'll show the class. That's okay. Did it all change? No. Homework 2. You February 1, Tuesday. So any general comments on what's going on, or anything you would like me to do differently? Aryan and Abdullah, is that used to the new system here? Like, what are the new things that come up? I think probably the email server, I think that might be the new thing. How is the teaching going for you guys?
It's nice. I've got some good students.
Okay, okay. That's always nice. That's always nice. Yeah. Yeah. Have you taught before?
Yeah.
Yeah.
Finance.
Okay, so that should help. Yeah. And you said you also taught, right, Aryan?
That is easy, but brains.
Oh, lab is easy. Grading is hard. Do you mean hard, or is it boring?
There are a lot of papers I have to do.
Oh, yeah. How many hours? I mean, yeah, this came up last year also, and at least when I looked into the assignments, I didn't see significant changes. But then I did mention it, by the way. I did bring this point up that for some people the load is higher, but I don't know what the limitations are. Usually there are limitations, not intentional, but you should, I would say, don't hesitate, especially, I would say, at least when I came here first, I'm culturally, I was from India, and it was not very polite to mention that I'm doing more number of hours. I'm sure even in every culture there could be misunderstandings. Be careful with whatever you do. But when you get a chance, you mention that you are doing too many hours. And if it is too much that it is hurting your classes, then you should bring it to that in a polite manner so that it doesn't bother. And everyone is trying, I think everyone is trying to help. Usually it is the ignorance. They don't know that you're actually working harder. So bringing it to someone's attention is good. You can try to bring it to me, but I can try to take it up, but I may not have the power to do it. And that's the best I can do. It did happen last semester, and it got resolved probably, but I'm not sure in the best manner. It hurts. So what's the? Tell me again how many hours you put in. That's the best. I can bring it up again, this question, and try to track the number of hours you're spending on grading. Is that possible?
I don't know exactly what
Roughly, I mean, yeah, that's good enough. And in fact, most probably the students only do an underestimate. Like if it is 10 hours of working, you're supposed to be, like when you do the calculation, it should come only 6 hours or something. That's the way I try to see. Try, yeah, that's a best, and I would say track the number of hours. And at least between us, I'm not saying that I'll solve the problem, but at least good that we point it out. If it's the same problem that we had last
Anyway,
Oh, Aliyah. Yes.
Yes. Hello, Dr.
Hello, Aliyah. Your volume is low, or is it this side?
Yes.
Rob, can you say something?
Hello.
Yeah, so maybe now it should be better. So Aliyah, where are you? So are you back in the country, in the United States, or are you still?
No, I'm in United States. We arrived on Monday.
Okay.
Yeah.
Yeah, sorry to hear about family. Yeah. Okay, so I think this will help you, I guess. I think you know everyone, at least 3 of you here, right?
Mhm.
I'll show you the new faces. You see Rob, I presume.
Mhm. Yeah,
You
hello.
recognize anyone with the mask? So we have Luke and Michael in the front desk. I think seniority works, I guess. The first row is the seniors, and the second row is the new students, Aryan
Abdullah.
and Abdullah.
Nice to meet you.
Thank you.
Yeah. Yeah. And that's Ali. Yeah, okay, nice. So okay, we'll come back. First, let me step this. So the recordings are there on the website earlier. So try to catch up with whatever did. So 2 weeks we did a review of Newton's laws, so that should be easy to catch up. And last class we did functional derivative. That might be new. So that's what you want to. So if you take my recommendation, start from last lecture, and others probably you can catch up. And it's not completely related. That's what I'm trying to say. But take guidance from others too. Robin, Luke, and Michael, and Aryan, and Abdullah. Okay. So
Okay,
let me. Okay, so we're doing functional derivative. We already introduced the idea, but we want to do some examples. And while we introduce the idea of functional derivative, we introduced delta functions also, which I presume that you're familiar with, but it's good to review some of the properties of delta function also. Note, so let's begin by a let's say vectors. This was a basic idea that if you were to do a gradient of x dotted with a, so this is not functional derivative, this is a normal derivative. This is a gradient, could be three-dimensional. There's an x, you would say this is equal to, but a is a constant, not explicitly writing that. And this is a. If I were to use index notation, this is I, and this is j. Right, this means that there is a summation in j, and when I take the derivative with respect to j, it's a derivative of x with respect to y is if x and y are independent variations, then they do not contribute. And that's equal to, let me say, actually in the first line, let's write this in two steps. There is a 1 here, a, and that's equal to a, where I've used the fact that gradient dot x, it's not dot. Similarly, here this is equal to delta ij, aj is the same as ai. These two are the same concept done in two different notation. This is using index notation. This is using the dyadic notation, which is pretty much the same as vector notation, except that there is outer product property that you have used. Okay. If you have a feel for this, what we did was we tried to convince that if we go into a continuous variable space, or is a function of space. The functions then we introduced the idea that instead of I and a j, instead so the gradient of u of x, let's say. This is the idea of this is a derivative of xi, right? So this is the ith x component, if you want. So instead of I, now we say this is y. So sorry, x. X could be any value, that particular component, if you want, or that particular value of u. Instead of this being a sum of linear terms, we now integrate this. This is a continuous sum. This is x prime, and it could be again u of x prime times a x prime. And this could have gone from A to B, or let's not say A to B, because we're using A there. Let's say so A, B, C to D, let's say. That's equal to, take this in, everything is x dependent here. This is, sorry, x prime dependent here. This is x, you can take this in. So let's C, D, x prime term of u x prime over x times a x prime.
Did you maximize this?
Oh, maximize the screen. Yeah. So you will see this. Oh, you mean this maximum? Oh, you just want this, correct? Oh, do you want to maximize this also? It's good to see faces, right? Yeah. Yeah. Okay. 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 Well, this is the analog we have of this quantity here, derivative with respect to x, or this one step in between, right, where the parenthesis changes. And next, you use the idea that variation of u of x prime respect to u of x, that's the way you would say it. This should be yeah, variation in u at x prime due to a variation in u at x. Is that independent or not? And we are saying it is independent. So we say this is delta of x minus x prime. That's where the delta function shows up. That's the analog. Here we have used I xj is equal to delta. If x and y are the same, or x1 and x2 are the same, then it's okay. Otherwise, it is equal to 0. I think I should say xi and xj. If that is the case, then immediately we learn that this is equal. This is a delta function, and that's equal to a of x. That's the main.
So you said that is the variation in u at x prime due to the variation at u of u at
At
x.
x. Okay. So let me try to draw that. And so let me write this first. So this is a variation in u at x prime due to a variation in u at x. So think of if you have three there's a vector which depends on 3 points. So you say this is 1, 2, 3, right? A1, A2, A3. So this could be I, and this could be 1, 2, 3, and this is A of I. So you say this is A1, this is A2, and that's 3. That's how you can represent a vector. And then you say that, okay, what if I change one, like A1 depends on some quantity. If you make this change, then due to a change in this, what is a change in that? Right, that's what you're saying. If you make a change in A1, does A2 change there at all? Right, that's the quantity we are saying. It's better to look at this as xi, not ai. I think this is, but then this would bother that. So let's say this is u of I. A of I instead of A of I, let's say this is U of I. And then you ask, what is a change in U1 due to the change in U2, right? The 3 vectors can be independent. Here, x1 is independent of x2. So the du1 I over duj is equal to delta ij. Unless I and j are the same, that's equal to 0. Like that's the statement you're making. But what is this? Now we are saying this is continuous, right? This is discrete. Now we want to say this is continuous. So this is x. Whatever is I, that becomes an x. It goes from C to D. It could be minus infinity to plus infinity. Nothing wrong in that. And now, so this is u of x. And that is a function. Okay. This is a function of x, and you would like to change this function. So now we are not changing a variable at this point. We are actually changing the function itself. And if you imagine, so you can, the easiest way, you would say that, okay, I make the change somewhere here, small change in there. And you're asking, when you make a small change at x, so that's your x, what is the change in x prime? So this could also have a variation in there. And these two needs to be independent. Whatever you do, these has to be independent. Unless you're on the same point, then you, I mean, if you change one, of course, you change the other one also because they're identical. Otherwise, they are independent. And you want to capture that exactly like this. It's 0 every time I is not equal to j. If it is equal to j, then it is not 0. Let's say that. So that idea here, so the variation in general, so let's say this is the random variation, right? Every point is varying. And that we say is this information. Variation in u at x prime due to a variation in u at x. And we're saying that those are independent variations. And they cause the function to vary completely. Could be the case. Is that clear? Any questions on that? There was a question in the quiz question was that, okay, so in this way of looking at it, it is 0 every time. And when it is the same, it is 1. Why can't we do the same thing here? It is 0 every time. And if they are identical, then it should be 1 over 1, right? So that it should be 1. That is what intuition tells us. But there is a challenge with that, because overall, if you remove 1 point, so let's, so this is the idea of delta function, right? Why we need a delta function to be at infinity? Why can't it be just 1? So, yeah. Yeah, this, let's begin with this itself, right? It is, when you have a delta ij, it is not just that I is equal to j, it is 0 and I is equal to j, it is 1 and I not equal to j is equal to 0. We also need the fact, we would also like the fact that this is equal to xi, or in this case a, right? A is equal to ai. When the Kronecker delta acts on a vector, it acts like an identity. It gives you back the vector itself. We would like that feature to be in there. So what are the two properties in there? One is delta ij is equal to 0 if I is not equal to j. That's the first thing. It's 1 if I is equal to j. And this property here, let's say summation of j times delta of ij times aj is equal to ai. Right? This says that at least one of them survives. Right? Out of these three sums, when j is equal to 1, 2, and 3, at least one of them will always be equal to I, and that will give you your ai. Right? So that's important. In matrix notation, you see that one identity multiplied by a vector is a vector itself. You would like both these properties to be satisfied. We want a similar concept in here. So delta function now. So this is delta function. Let's the way it is defined as an analogy here would be it is, first of all, x minus x prime. This is I and j is taking the values of x and x prime. This is equal to 0 if x is not equal to x prime, if having a function of that kind. And if you go pretty much like that, let's say this is 1 maybe, let's say 1. Let me put a question mark here because I'm going to change that value. Let's say x is equal to x prime, and I would also need this. Right? I also at the same time would like the same property in there, and there the idea is that this is equal to, let's say c to d, it doesn't within some boundary, dx prime, and same property delta of x minus x prime multiplied by some function now. This is a of x prime should give me a of x. Okay. If you look at this, what this means is I have a x. This is delta of x minus x prime. Somewhere there is a value x and there is a value x prime. Right? This is x, there is x prime. Or maybe I should say there is the best way to say it is I'm integrating over x prime, so that's a variable x prime, and somewhere there is a special value x. At x, whenever this x prime, the one that is scanning, the x prime variable is equal to x, that's equal to 1, otherwise it is 0. So your function here is 0, 0 everywhere, and somewhere here there is 1, right? So I'll show it like this. It's just at one point, there's 1, everywhere else it is 0. There is another function a of x prime, and let's presume that that's a normal function. By normal function, I mean it doesn't go to infinities anywhere. So a good, nice, well-behaved function, let's say. So that's a simple function. Let's say this is this. That's here. Any arbitrary function a. If I multiply these two functions, notice, so I have, so this is their new function now, so that's a fx prime multiplied by delta of x minus x prime. You multiply those two functions, it's clear that it's 0 everywhere. This is 0 everywhere. And a of whatever is the value at x here, multiply that with 1, and you get 1 point here, which is a of x multiplied by 1. So that's this point value here is a of x multiplied by 1, which is just a of x. Is that clear what I'm saying? We would like to find the area, and it is 0 everywhere else because you multiplied by 0. Integral of a multiplied by delta function, integration of that will be the area under that function. What is the area under a function which is 0 everywhere, and it has a value 1 somewhere at that point? What is the area of such a structure? It is 0, correct? So it is exactly, if you, and the idea is, let me do other. So the basic idea is you have, let's take any function f of x. If you were to go from, let's say, a, and you go to a plus delta, and this is your area underneath this. And if I have an integration to do f of x, and then you go from a to a plus delta, and then you talk about whatever, however you do it, this will be equal to, in the extreme limit, that's just a rectangle. In the extreme limit of delta tends to 0, limit delta tends to 0, that is a delta, a plus delta minus a. So the base is delta, right? That's length into breadth, right? So this is length and length into height, let's say length into height. What's the height of this rectangle? That's f of a. So it's a very small number multiplied by a finite number. Unless f of a is infinity, these two cannot give you anything other than 0. This is equal to 0. Unless, right? Unless f of a itself tends to infinity. If it is infinity, maybe it is not, I mean, it need not be something finite, at least it need not be 0. It could grow. So that is, it will be 0 for sure, unless this grows. But we have said that this is a nice function. This is a of x. So this is actually finite. So there is no way you can get a of x, right? I cannot integrate this and get back my a of x, because a of x is going to be multiplied by that tiny delta in that limit. So you cannot get a of x. So this does not get satisfied if this was 1. But then when you say, okay, so what should it be? So you, I mean, it is not clear that an infinity will satisfy either, because the moment you say infinity, there are different kinds of infinity, how something grows. Right? So for that purpose, let's look at this more closely. Let's say what kind of growth might help us. So, so let's take an example. So simplest example how you can have something grow is, let's have a plateau like structure. So this is your x, and what did I do? Yeah, this is your x, let's say. this is 0, x is equal to 0, like this is your h or delta. That's your delta. But now I say that the height of this plateau is not arbitrary. It is, so this is height, this as a height, is exactly equal to 1 over delta. And remember, this was just f of x. And now I do the integral again. It's very similar to integral I was doing there. So this is x, let's say, minus infinity plus infinity. It could be some c to d that is enclosing this region. So that's dx times f of x. And this time you say that, oh, that's the area underneath this curve. So this is just this. I don't have to really, I mean, that's the only way to do that integral. Right? It is 0 everywhere. Hopefully this was clear. So the function I'm defining is 0 everywhere except, let me specify this. This is equal to 0 if x is less than 0. It is equal to 0 if delta x is greater than delta, and it is equal to 1 over delta if x is greater than 0 and less than delta. That's the definition of that function. And then you see that, oh, this is however you define it, those were details. It is just the area under that rectangle, and we know what's that area. Area is length times height. So it is delta times 1 over delta. And of course, you want to take a limit, right? This is even in the limit, delta tends to 0, right? This is okay. Right? Even in the limit, delta tends to 0, delta cancels out, and that's equal to 1. So only for that special case. So let's just for the sake of showing that that need not be 1 all the time. So this is example 1, right? Say example 2. Like this is one of the basic infinity that it is 1 over x. Right? It's growing like 1 over x raised to minus 1. If my function was here, height was equal to 1 over delta square. And that's a possibility. I could have had 1 over delta cube, 1 over delta 4. All those are possible heights. Right? Now, integral minus infinity to plus infinity dx f of x is equal to limit delta times 1 over delta square, and this time that grows to infinity. So that's just a clarification that not every infinity is acceptable. Only those infinities which exactly cancel the 0, that is a 0 multiplied by an infinity. So when you say 0, it is not really 0. You have to ask the question, how does it approach 0? So both zeros and infinity have a structure inside them. Whenever you say something goes to 0, you have to ask how quickly something goes to 0. Like exponential approaches 0 in a different manner than a logarithm function approaches 0, or a sine function approaches 0 differently than cosine function. Cosine function goes as 1 as you go, x tends to 0. Sine function goes to 0 as you approach 0. Same thing at infinity. How quickly you approach infinity matter, and it is that balance, that the approach of 0 and approach of infinity, if they are canceling each other, they are very fine situation when they balance each other. So you can multiply a small number and a large number, sometimes very rarely, and get a finite number. And that's what we are looking for. And it's surely an infinity. So as I said, unless f of a is infinity, but not any kind of infinity, it has to be something that matches this 0, exactly, that gives you a 0 multiplied by an infinity gives you a 1. So this seems very hand waving, right? So let's have an actual function which does that. So that should be more more elegant in a sense. So
2 is not covered.
oh, you guys need to, thank you. You guys need to buy a treat to Abdullah because okay, now how do I call it? Better? Yeah, Rob and Elliot, tell me. Okay. Yeah, sorry, I kept going. Yeah. But yeah, thanks, Abdullah. Yeah, that sounds okay. Actually, for all of us, right? I mean, when we go back, I mean, there was this recording yesterday. Yeah, yesterday I did this in the auditorium, and these are undergraduates. I don't think they will appreciate it at all. So I started the lecture, and this is a big lecture. I started on the right side, writing this homework 1 and other things, and then I forgot about the whole camera. So I'm writing everything in here, and then I go in there, and then after I finished the whole board, then I realized, oh, no, after that, I came back to write this board, and I started erasing. After erasing, I remembered that, oh, I forgot. So let me take the camera, and oh, I forgot, I erased it, right? So there was no recording. And I don't think undergraduates will really appreciate that. So what, yeah. So, I couldn't do much. Yeah. Okay, so with that idea, so this is again, one might say that, oh, that's not really a smooth function, right? You're breaking things. It's not very elegant when you think of a function, your exponential Gaussian type of function. So let's have a more concrete structure. Again, the basic idea is that it should be 0 everywhere other than 1 point. It should be, now we have established that it should not be 1, it should be infinite. Right? It has to be infinity, a special kind of infinity, but it has to be an infinity. And third, when you do the area underneath that, it should come out to be 1. Right? If you just have a integral, it should come out. Those are the 3 properties a delta function has to satisfy. So a simple example could be, so let's say f of x. This time I should forget change. Have you guys copied? Robin? Oh, okay. Thanks. Okay. So let's have this to be x over I think it is. Yes. Delta. X is not equal to 0. I mean, x is equal to, yeah. And this is the limit delta tends to 0. And I think that is a pi, or 2 over pi. I think it's a pi. Maybe I'll come back and write it 2. There's some normalization requires a 2 over pi. We'll get that fixed. So as I said, I'm claiming that this is a delta function. So if it is actually if this has all the properties of a delta functions, then it should satisfy those 3 conditions, right? How does this look like when you plot it? I claim, let's say when x is equal to, let's say when delta is not equal to 0. Then x is equal to 0, it is 1 over delta, so it is height is about 1 over delta, right? So there's 1 over delta coming in there. And then x is somewhere large, so this dominates, so that's delta over x squared. So this probably looks like this. And this is 1 over delta. It turns out that this, how much the spread is, that's about delta. And that's always needed. Again, the same property, like the base should squeeze. When you squeeze the base, the height should increase, right? That's the basic idea of delta function, but in a very specific form. Its growth should be decided by or linearly grow as the base goes in. So let's see what happens. So let's say what is f of f when x is not equal to 0, right? X is not equal to 0. What happens? So if this is not equal to 0, that means it can be greater than 0. F of x is in the limit delta tends to 0. Surely, since x is not equal to 0, this will dominate eventually. Right? The denominator x square will dominate. So it is limit delta tends to 0, 1 over pi times delta over x squared. Because sum of two numbers where x is in the limit delta tends to 0, x will always be larger. But this is finite, it's not 0. So the numerator is small, so this goes to 0. That's good. So whenever x is not equal to 0, it is 0. Right? That's the property of a delta function, right? It should be 0 everywhere except one point. So it is turning out to be x equal to 0. Let's say what happens at x equal to 0. So then f of x is equal to now x is exactly 0. This is delta tends to 0, 1 over pi, x is 0, so that's delta over delta square. Take the limit again. This time it surely grows to infinity. So that's the second property that it should be large. One says that it should be 0. When x is not equal to 0, when x is equal to 0, it is large. But now the product of these two quantities, which is the area, 0 times infinity, that should be a finite number. And for that, we do the integral. This is dx, x, let's say minus infinity to plus infinity. So that's if you take the limit out, limit delta tends to 0. The order of limits matter when you take the limit. That's important, exactly like calculus. And here we're doing the summation first and then taking the limit delta tends to 0. So this is the x, and this is delta over x squared plus x squared. That's minus infinity to plus infinity. This integral, probably you can use tangent theta. Substitute x is equal to delta tangent theta. So dx would be equal to delta secant square theta. Okay. So do the integral or do the substitution. Limit delta tends to 0, 1 over pi. When x is equal to minus infinity, tangent of minus pi by 2 is minus infinity, right? So this is minus pi by 2. And when x is equal to plus infinity, then theta has to be pi by 2. dx is delta secant square theta theta. That's dx. There's a delta in the numerator, and in the denominator, you have delta square tangent square theta plus delta square. Nicely, the delta square cancels out, so that's the nice feature. See, that's what tells us that, oh, this is going to give us a finite number. All the deltas, which is going 0 when it is in the numerator, and because if it whenever it is in the denominator that diverges, that has to balance out. Right? That's so often this can be seen by counting powers itself. Oh, this goes to 0, that goes to 0. So when you collect all together, This is called cancellations of infinity. So this is 2 deltas in the numerator, 2 deltas in the denominator. They take away all the features of going to 0 or infinity. So we keep delta tends to 0, even though in this step this will go away. This is minus pi by 2 plus pi by 2 d theta. Numerator has secant square theta, and denominator has tangent square theta plus 1. All the deltas are gone. And then you see the feature that, oh, nice, this is the same, right? Trigonometric identity tells me that 1 plus tangent square theta is secant square theta. Integral of d theta then is trivial. So that's pi, and I did choose my normalization correctly. This is pi, that's come out pi, and this is indeed 1. This is a demonstration that the 0 times infinity is actually 1. So not very cleanly. It doesn't happen very cleanly only when these kind of structures come together. That gives you a 1. And that's the idea, and that is the reason why that infinity is there and it's not really 1. But the basic idea we are trying to stress here is that all that to convince that that's a delta function. So we are basically saying again in functional derivative. So that is derivative of xi with respect to xj, right? And I'm not being careful with whether it is a covariant or a contravariant, but that's a vector, or whether the index is in the subscript or superscript. This is equal to delta ij, right? That's your discrete derivatives and functional derivatives in the same spirit. This x prime, and so let me write that in this form. That's delta of x minus x prime. That's the analogy you want to keep in mind. The way this is equal to delta ij, the same spirit, this is equal to this, with the additional feature that here when I was equal to j, this is equal to 1. So this is equal to 1 if I is equal to j and 0 otherwise. One if I is equal to j, 0 otherwise. And here it is equal to infinity if you want, tends to infinity. Tends to infinity if x is equal to x prime and 0 otherwise. That's what we have talked. Any questions there as of now? Okay, once you have, yeah, I think that's all. Yeah, maybe a quiz, right? I'm not going to do that here. It's good to save time. I won't do that yet. You guys are submitting quizzes. Well, so I'll put something in quiz. So we have sort of clarified. Let me keep minus infinity to plus, let's say ab x yeah, f of x times delta of we have mostly what we have done till now is this, right? I have tried to convince you guys that that's actually the statement of delta function. Then it is good to ask, what if you have derivative of a delta function? What is that equal to? If you succeed you convince yourself what that is equal to, then you should ask what is x prime square, or second derivative of delta of x prime. What is that equal to? And if you succeed in that, then you keep going, right? So fourth and see the pattern. Like what exactly is this equal to? So this is a quiz. I should do this first, but something there. Any questions on what the quiz is about? Okay. So with this machinery in our hands, let's try to do some examples on functional derivative, and that's what your whole homework is about. There is a bunch of examples here to do, and there is one problem which is descriptive in the sense you try to actually minimize and try to try to do a problem in variation of calculus. So, example. Let's say I is equal functional. This is the functional. So let's say the name, so f functional. You say f as a function of u. Let's say let's say f of u is a, yeah, let's do the earlier one first. We already did this, but why not repeat? That was already done in the language of functional derivative. I will say functional derivative of f, function of u of x. And I keep this as x prime so that I can use the x outside. That's the basic. This is equal to a to b dx prime. As I said earlier, u of x can go into the integral u x prime times a of x. You realize that this is a delta function, and delta function immediately gives me a of x. So that's we already clarified this multiple number of times. Example 2, which helps you with the quiz that I gave just now. F of u is equal to a to b x prime.
Rajesh, would you please move the camera?
Oh, yes.
Thank you.
Yeah. Thank you for pointing out. Okay. So example 2, the functional, we say this is functional. Here is u of x prime. Yeah. So this is, let's say this is d u x prime over, this is the derivative of u that is showing up, and just to make sure that it is clear that the derivative is acting only on u, I put those curly brackets times a of x prime. Okay. Again, I want to do the functional derivative, and I'll do the same idea. So this is f of u and u of x, right? That's what the functional derivative means. Again, remember, physically what we are saying is that this quantity depends on the function u. Out of all the functions, if you make a change in the quadrant, what do you get? That's what you're trying to say. It's like saying if you have x and this is your u, so that's your u of x, but there are lots of possibilities in here, right? So that's your another u. If I make a change from this to this, how does your f value change? That's the question here asking. And later on, we will ask the question, is there a possibility that you make a change in u, but f doesn't change? Right? That means that it is 0, right? That's what the stationary will be, right? Stationary condition. So that's a physical meaning of that, but currently we are just practicing how to do the functional derivative. And now you do the same thing. This is with respect to x, right? As far as we are going with x, you can penetrate the integral. In fact, you can even penetrate the derivative. So this is a, b, x prime, d by x prime of, let me write this. So this is u of x prime over x. And say like this. Now that's a of x prime. If this quantity here, that's delta function. That's our identification, and that's equal to a e x prime of delta of x minus x prime or x prime minus x, doesn't matter, times a of x prime. And if you see, that's exactly the question you had in the quiz, right? In the quiz, we asked what's the derivative of this, and I will show it as a result. You in the quiz, you worked out, right? I mean, check it out. And in fact, exactly like delta function of a function is the functional value, derivative of a delta function gives you the derivative of the function. So maybe I should do this once, right? Why jump at step? So let's proceed and actually calculate this. It's only two steps. If I have a derivative, I know how to evaluate delta function at this stage, right? I don't know how to evaluate derivative. So remove the derivative from there. How do I do that? If I want to move the derivative from here to there, I do integration by parts. So I do integration by parts. So this f of u of delta of u of x is equal to integration by parts a b x prime. And the way I will do the integration by parts is instead of hitting only the delta function, I'll hit both. So this is x minus x prime times a of x prime. It is not correct, right? This is not the same as what I did, because here it is acting only on delta function. There it is acting on both. So there is a difference between the two. Subtract the difference, and that is minus of a to b prime. What did I miss here? When I hit this, that is my left hand side, or the side I began with. So what am I missing when I hit a derivative of a? Minus x prime times okay. This is a total derivative. Right? This is a total derivative in the sense that these two cancel out. That's d of something, right? Change in d. So whenever you have integral of d of f going from a to b, this is f of b minus d of f. D of f, it's f of b minus f of a. right? That's a total derivative. So this is, you will evaluate this at B and A. So you're equal to evaluate this function of x minus b times a of b minus of delta of x minus a times a of a. Not a good choice, a and b. This a and this a is different. Like, I should be careful. This should be C and B. Okay, so let's not change it. I think it's contextually clear. Okay, so allow me that. And this is just a delta function now, right? This is normal delta function. Whatever is on the right side, whatever is beyond delta function, that's what it evaluates to. So this is d by dx of a of x. Unless this x is not within a and b, that's a possibility that x is actually outside a and b, then it doesn't contribute at all. So there's a small caveat there, but assume that x is, let's say that x is less than b and greater than a, then there is always a value in. But now, if I say that x is always less than a or less than b and greater than a, what is delta of x minus b? It is 0 because it's not equal to b. The only place when this contributes is when it is at x equal to b, and at that point it is very large, right? It is almost, it is infinity. So this is 0 because of this condition. As an added condition, I'm saying that x here has to be in between a and b. So this is equal to 0. Same thing here, this is also equal to 0. What that is meaning is that, remember again, delta function, if you were to interpret it in this form, or we'll come back to that. So this is now equal to just minus derivative of a of x. So practically what has happened is that when there is a function, you just get the function itself. When there is a derivative of u, functional derivative of u with respect to a derivative of u, it gives me the derivative of whatever is remaining out there. So it just moves it to the right. We said this is 0. Let's have a physical interpretation of that. Oops, again, I forgot it. Yeah, almost. We said this is equal to 0. Let's have a small interpretation of that. So delta of x minus b, where x was running between b and a. Like there was boundaries f, a and b, and what we are thinking of is that there is x. So this is a, that's your b, and you have a function which is u of x. Correct? So this is u of x, which goes okay. Okay, so this is can be thought of as change in u of b over change in u of x. And you might always ask, oh, is it so change in u at point b, right, due to a change in point somewhere else at x? Like make a small change in u and ask what is the change in b, right? In general, it is possible when I make these changes, we can actually make the whole function change, right? This is also a possible change. So this is a possible change in the function. So this, even though we interpret it as, oh, that doesn't contribute, that should be interpreted as the boundary. There is no variation at the boundary. So this should be interpreted as no variation NU at the boundaries A and B. That's not that always we will put that. We will sometimes, we would like to have information about the boundary. In fact, we will see that there is a good amount of information at the variation at the boundaries. Even though most of the Lagrangian mechanics will come by keeping the boundaries fixed, we will see that if we don't keep the boundaries fixed, there is very good information. In fact, there is a lot of symmetry principle, or the conservation principles will come from the boundaries. And there will be a nice interpretation there. That's the idea of canonical transformation, and it even goes into quantum mechanics. We'll try to do as much as possible. Or let me just, how about quiz, right? You could figure it out. We'll come back and do this in about maybe 3 weeks or a month. The question is, how is a variation at the boundaries related to conservation principles and the associated symmetries. The actual word for this is Noether's, I don't know how to pronounce this, Noether's theorem. Have you guys come across the word Noether's theorem? So that's that comes from this variation in the boundaries. Okay, I think rest of it you're on your own in the homework. So I did the most simple examples I did, you do the hard examples. But the basics are there, so you should see.
So this means that we don't change the value of the function as boundary.
At the boundary. That's a choice we have, but we can. So unless it's given to you that do not change, you should change. In general, you can change. But in the beginning, about 1 or 2 weeks when we're doing Lagrangian mechanics, we will keep it fixed just for making it easy. So first we'll keep it fixed and get, that is what Euler-Lagrange equation and Newton's equations of motion always comes from keeping the boundary fixed. But then we say, I keep it fixed, let's change it. Is there any information in there, right? There will be no stationary action principle in there because now it's not stationary anymore. But then we say that, okay, what can we learn? And that's basically the statement of Noether's theorem. And it's kind of beautiful, very powerful, if you want, that we can say, what is a momentum? What if momentum, or what if, I think the question you ask is, if you make a transformation, like you're in this room, and the way I usually tell is that you sleep, and during sleep, someone comes and moves everything, like this room is moved 1 meter, you are moved 1 meter, everything that is built out of this room is moved 1 meter to your right, let us say. And now you wake up, is there a way, can you do an experiment and verify that actually you moved 1 meter? Right? And that depends on whether the system conserves momentum or not. So that's connected with momentum conservation, which is not trivial at all, right? You moving 1 meter, what has it got to do with? And that will come with this variation when we say we'll actually go to the position and then make a small variation in A, and then ask what changes to the Lagrangian, and then we will be able to say that this has to do with it. So that conclusion is has some 2-3 steps. After you learn all this jugglery, with variations, then eventually there are some two steps logically. One can conclude that if this happens, then this has to be true. So that's a deduction one can make. We will reach that. And similarly, rotations. If you rotate this room instead of translation, you rotate this room, then angular momentum has to be concerned. Those kind of conclusions will come out. The whole, it's called a point ray symmetry that we'll try to do. And there are many such conclusions you can make. The virial theorem in astronomy, astrophysics, I think, that comes from the same principle, or you can, it doesn't come in, like originally it was, of course, not, they didn't use all this machinery for that, but you can get virial theorem from the variational principle. So very powerful tool there. So we'll try to do as much as possible that surely rotations and the translations in time and translation in space, those are the point ray symmetry that we will try to cover. And that should take a good amount of time. So that's a broad little bit of advertisement for what is there in store. And I also like to do a little bit of, even though I say that dissipation cannot be handled, friction usually cannot be handled in Lagrange, or it cannot be done in the straightforward manner, but you can, in the sense, if you do some, again, tricks, you can actually, so that's called Lagrange multipliers. So I'll try to introduce that also, very little of that, at least do a few examples where clarification is there for all the bigger examples we'll allow to leave. So that's what we will do in the next few weeks. Okay, thank you.
Thank you.
Oh, I should change the camera so that you guys can see each other once more. So you're in your office earlier then, right? So this is Nekas?
No, I'm at home.
Oh, you're. I shouldn't be looking at the background. That's privacy. Yeah. Okay. So your kids are back?
Yes,
Sure.
now they are in school.
Ah, relief, huh?
Yeah, that's why my
You can
background.
concentrate. Okay. Okay, guys. Yeah, shall I shut down, Rob? Anything? Yeah. Okay.
Thank you.
Okay. Sure. Yeah. See you earlier sometime. Yeah.
See you. Thank you so much. Bye.
Yeah.